Hello, my name is Ron Russell M. Caparsan. Today, we'll be doing the finals on microprocessor. There are 5 topics to discuss. The first one is the how CPU works. Second one is the evolution of CPU, part 1 to part 4. Next one is the overview of GPU. The next one is the SAP1 operations. And lastly, SAP1 programming. The first one is how CPU works. A CPU is the core component of a computer or any device that performs the main operation needed for computing. It's often referred to as the brain of the computer because it handles processing tasks from simple tasks like typing text. Complex activities like rendering graphics involve the CPU in some capacity. What is the role of the CPU? The role of the CPU is responsible for carrying out instruction from software programs by performing basic arithmetic logic, control on and input-output operation. When you run a program, the CPU interprets the program instruction and carries out the necessary operations. Next one is how the CPU fits into the computer system. Interfacing with memory. The CPU communicates with the system memories, RAM, to fetch data and instruction for processing. It relies on the memory hierarchy. Example is register, cache, main memory to store and retrieve data quickly. Next is the control of other components. The CPU not only processes data but also manages the interaction with other key components such as input-output device, keyboard, mouse, screen, storage devices like hard drive, SSDs, and peripheral hardware like graphic cards, network adapters. Processing instruction. The CPU processes instruction provided by software, and through its execution of this instruction, it allows the user to interact with the system. Example is the open programs, load website, run games. There are components of CPU. The control unit is the first one. The control unit is responsible for managing the flow of data and instruction inside the CPU. It doesn't perform calculations itself, but it coordinates the actions of the arithmetic logic unit and other components. This control unit ensures that the CPU follows the correct sequence of operations, fetching instructions from memory, decoding them, and then sending commands to the arithmetic logic unit to execute those instructions. Key function of the control unit. Number 1 is the fetches instruction from memory. Number 2, decode the instruction to determine the required operation. 3 is sends control signal to the other parts of the CPU and other components in the computer to carry out those instructions. The second one is the arithmetic logic. The arithmetic logic unit is the part of the CPU responsible for performing mathematical logic operation. It can perform tasks like addition. First one is the arithmetic operations: addition, subtraction, multiplication, division, etc. The next one is the logical operation, which can be comparison, greater than, equal to, less than, and or not operations. In essence, the arithmetic logic unit, the actual processes the data processes the actual data like performing calculation or making decision based on condition in the data. Number 3 is the registers. Registers are small, high-speed storage locations inside the CPU that hold data temporarily during processing. Registers are used to store operands, the data to be processed, and intermediate result. There are several different types of register. Number 1 is the general purpose register, used for storing temporary data during program execution. Number 2 is the special purpose registers. These include the program counter, which tracks the address of the next instruction to execute, and the accumulator, which often holds intermediate result from the arithmetic logic unit. Register plays a critical role in speeding up CPU operation, as accessing data from register is much faster than fetching it from main memory. Number 4 is the cache memory. Cache memory is a small but very fast type of memory that stores frequently accessed data and instruction to speed up the process. CPUs typically have multiple levels of cache. L1 cache, the smallest and fastest cache located closest to the cores. L2 cache, larger and slightly slower but still faster than main memory. L3 cache, even larger and slower than L2 but still much faster than RAM. The use of cache memory helps to reduce the delay when accessing data from RAM and significantly boosts overall CPU performance. Number 5 is the clock. The clock is a timing device within the CPU that synchronizes the operation of all components. It sends out regular pulses at a consistent rate, known as the clock cycle, which dictate the speed at which the CPU processes instructions. The clock speed is usually measured in gigahertz, with higher clock speeds meaning the CPU can process more instructions per second. Number 6 is the bus interface unit. The bus interface unit is responsible for handling communication between the CPU and the rest of the computer system, especially memory and input-output device. It uses data buses to transfer data to and from the CPU. How the CPU works. The operation of the CPU can be broken down into a repeated cycle of fetching, decoding, and executing. Number 1 is the fetch. The CPU fetches an instruction from memory. The address of the next instruction is kept in the program counter. The instruction is transferred from memory to the instruction register in the CPU. Number 2 is decode. The control unit decodes the instruction to understand what actions need to be performed. This involves determining what type of operation is needed, arithmetic logical data movement, and what data or memory locations are involved. Number 3 is to execute. The CPU executes the decoded instruction. If it's an arithmetic operation, the arithmetic logical unit performs it. If it involves data movement, the data is transferred to the correct location. The arithmetic logic unit may also update registers or flag based on the operations. Number 4 is to store. After the instruction is executed, the result is either stored in a register or sent to memory, where it can be used by other parts of the system. And next is the type of CPUs. Single-core CPUs. These have one core capable of executing one instruction at a time. Multi-core CPUs. These CPUs have two or more cores, allowing them to execute multiple instructions in parallel, improving performance and multitasking capabilities. Next is the dual-core, quad-core, octa-core CPUs. This refers to the CPUs with or 4, or 8 cores respectively, allowing for more efficient multitasking and parallel processing. Next is the ARM and 86 processor. These are the two different architectures used in CPUs. ARM processors are often used in mobile devices and are known for their power efficiency, while 86 processors are common in desktop, laptop, and are known for their high performance. Next is the evolution of CPUs. Early CPUs. The first CPUs were relatively simple and operated at lower speed with very limited capabilities, like the Intel 4004 in 1971, which had a clock of speed of 740 kHz. Modern CPUs. Today's CPUs are highly advanced and are capable of performing billions of operations per second with multiple cores, high clock speeds, and integrated features like graphic processing unit, GPUs, or specialized hardware for machine learning. The shift to multi-core CPUs has allowed processors to handle more tasks simultaneously, improving performance for modern applications like gaming, video editing, and running complex software. In addition, specialized CPUs such as TPUs for graphics or TPUs for machine learning help offload specific tasks from the main CPU to enhance efficiency. The next topic is the evolution of CPU Part 1 to Part 4. During the mid-1960s, a revolution in miniaturization was kick-started. The idea of packing dozens of semiconductor-based transistors onto a single silicon chip spawned the integrated circuit. It laid the groundwork for a complete paradigm shift in how modern society would evolve. In less than a decade, this marvel of electronic engineering and material science would lead in an era of advancement incomparable to anything else in human history. In the March of 1971, the commercial launch of new semiconductor products set the stage for this new era. Composed of a then incredible 2300 transistor, the Intel 4004 Central Processing Unit or CPU was released. Initially created as a custom solution to the Japanese company Bisicom Corp for use in the Bisicom 141PF calculator. It was released later that year to the general public. With prophetic irony, the marketing material for the chip touted the slogan, announcing a new era in integrated electronic. But what made the 4404 so groundbreaking? Take a calculator and solve any simple arithmetic operation, let's say 12 divided by 7. What we just did was issue a computer an instruction. Instructions are elemental operations such as math commands that a CPU executes. Every computer program ever made, from web browsers to app to video game, is composed of millions of these instructions. The 4004 was capable of executing between 46,250 to 92,500 instructions per second. For comparison, ENIAC, the first electronic computer built just 25 years earlier, could only execute 5,000 instructions a second. But what made the 4004 so powerful wasn't just its 1,800 increase in processing power. It only consumed 1 watt of electricity, was about 3/4 of an inch long, in, and cost $5 to produce in today's money. This was miles ahead of annual cost of $5,005 million in today's money, 180 kilowatt power consumption, and 27-ton weight. Fast forward to September 2017, the launch date of the Intel Core i9-7980Xe. This CPU is capable of performing over 80 billion instructions a second, a 900,000 times increase in power processing. What did it take to get here? In this three-part series, we explored engineering and behind the science technology that paved way that the simple 16-pin chip to evolve into the powerhouse of CPUs today. In digital electronics, everything is represented by the binary bit. It's an elemental representation of two possible states, a 0 or 1, true or false, up or down, on or off, or any bi-state value. In a CPU, a bit is physically transmitted as voltage levels. If we combine multiple bits together in a group, we can now represent more combination of discrete states. For example, if we combine 8 bits together, we form what's known as a bit. A bit can represent 256 different states and can be used to represent numbers. In the case of a bit, any number between 0 and 255 can be expressed. But in a CPU, how we choose to represent data is completely malleable. The same byte can also represent a number between -128 to 127. Other expressions of that byte may be colors or levels of sounds. When we combine multiple bit together, we create what known as a word. Words are expressed in their bit capacity. A 32-bit word contains 32 bits, a 64-bit word contains 64 bits, and so on. When processors are created, the native word sites operate in approximately 1,100 words. Forms the core of its architecture. The original Intel 4004 processor operated in a 4-bit word. This means data moving through the CPU sits in chunks of 4 bits at a time. Modern CPUs are typically 64-bit, however 32-bit processors are still quite common. By making use of a larger word size, we can represent more discrete states and consequently larger numbers. A 32-bit word, for example, can represent up to 4.2 billion different states. Of all the forms data can take inside of CPU, the most important one is that of an instruction. Instructions are unique bits of data that are decoded and executed by the CPU's operation. An example of a common instruction will be to add two word values together or move a word of data from one location in memory to another location. The entire list of instructions the CPU support is called its instruction set. Each instruction binary representation, its machine code, is typically assigned a human-readable presentation known as an assembly. If you look at an instruction set of the most CPUs, they all tend to focus on performing math or logical operation on data, testing condition, or moving it from one location to another in memory. For all intents and purposes, we can think of a CPU as an instruction processing machine. They operate by looping through 3 basic steps: fetch, decode, and execute as CPU designs evolve. These 3 steps become dramatically more complicated and technologies are implemented that extends this core model of CPU operation.